All right, hi everyone. So in this video, we are going to continue working with magnitudes of vectors and inner products. And so one common thing that we may want to do is say, given a certain vector like this vector v that we've sketched below, and so v is the column vector -4, -5, and recall we've calculated the magnitude of this vector, which winds up being the square root of 41. And question 1 is asking us, let's find some vector w that has the same direction as v, but is twice as long. So we've got some vector which has the same direction, but is double the length. Well, let's consider what would happen if I were to take this vector v and multiply it by some scalar c, and we'll assume this scalar c is bigger than 0. If I pick a scalar c which is negative, then that is not going to give me a vector which has the same direction. It's going to give me a vector which has the exact opposite direction, so that points up and to the right. But we want to find the vector that points down and to the left, but is twice as long as w. So we can pick some scalar c bigger than w, and let's consider what happens if we want to find the magnitude of this vector. Well, we can write this as the square root of c times v inner product with c times v. And recall from our properties of inner products, we can pull out those constants, and we've got two of them. So I can pull out one c and I pull out a second c, and that gives me c squared times the dot product of v with itself. And now I can pull the c out from inside the square root, and normally we would have to put an absolute value sign here, but we are assuming c is bigger than 0. So out comes the constant c, and we still have inside here v dotted with itself. So this is actually equal to c times the magnitude of the vector v. So in other words, when we multiply a vector v by some positive scalar c, then the magnitude of that resulting vector w is going to equal c times the magnitude of v. So using this fact, we can now answer this first question. I want to find a vector w that has the same direction. So if I multiply it by some scalar that's positive, it will preserve the direction. And if I want to double the length of the vector, then the scalar that I should multiply v by would be 2. And that's going to give me a vector whose magnitude is 2 times the vector of v. So if I set w equal to 2 times v, that would mean we're setting w equal to -8 -10. And then you can check that if you calculate the magnitude of this vector, you'll get 2 times the square root of 41. So you get a vector which is twice as long as the vector v that we started with. In question 2, this is a really common question, and it's going to be really convenient to say, given a vector v, let's find the unique vector u which has the same direction as v but has length 1. And so now we're trying to find some vector v, or excuse me, u, that has the same direction, but now this vector u, it has magnitude equal to 1. So we can use the same idea, namely that, well, let's multiply this vector v by some appropriate scalar. And in this case, we can use the fact that this vector v that we started with, its magnitude is the square root of 41. And so now if we want to construct a vector u whose magnitude is equal to 1, then we should scale this vector v by 1 over the square root of 41. I want to make it smaller. I want to scale it down by the reciprocal of the magnitude of vector v. So I can take this vector u, and the scalar that I'm going to multiply v by is going to be 1 over the magnitude of v. And the magnitude of v in this case was the square root of 41. So if I take 1 over the square root of 41 times this vector v, that means I multiply each entry in the vector v by 1 over the square root of 41. So that gives me a new vector u whose first entry is -4 over the square root of 41, and whose second entry is -5 over the square root of 41. So we scale each entry by 1 over the magnitude of v. And you can check if you calculate the magnitude of this vector u, you will indeed get 1, and this vector has the same direction as the vector v that we started with. So on the next slide, we are going to generalize this process about how we can find unit vectors in a certain direction. Okay, so a vector u, and this is a vector that could be any dimension. So this is a vector u in Rn, whose length is equal to 1, is called a unit vector. And so the process of creating a unit vector u from some arbitrary vector v is called normalizing vector v. And we say that u is the unit vector in the same direction as v. And from the previous example, we've seen that given some vector v, we'll assume v is a non-zero vector, that we can normalize this vector by scaling v by a factor of 1 over the magnitude of vector v. So this process is what's called normalizing the vector v, and this result u, we say, is the unit vector in the same direction as vector v. So let's take a look at an example down below. So recall earlier we considered vector v, which was in R3, the column vector whose entries are 1, 2, and 3. And we found that the magnitude of this vector v was equal to the square root of 1 squared plus 2 squared plus 3 squared, which gave us the square root of 14. And so if I want to find the unit vector in this direction, then that means I'm going to multiply v by 1 over the square root of 14. And when I multiply a scalar times a vector, that means we scale each component of the vector by 1 over the square root of 14. So my first entry is 1 over the square root of 14. My second entry is 2 over the square root of 13, and then 3 over the square root of 14. So now this vector u, which is 1 over the square root of 14, 2 over the square root of 14, 3 over the square root of 14, has the same direction as the vector v, and you can check that the magnitude of this vector is 1. So this vector u is the unit vector in the direction of v.